Hi, in this video we'll talk about line+noise model fitting. Recall that up to this point in the chapter, what we have talked about is this idea of a signal plus noise model, and the main signal that we've talked about so far is the line. So that's why we say a line plus noise is a type of a signal plus noise model. Next, in the next video, we'll talk about another signal called the cosine, but in this particular video, we're talking about the line plus noise model and how you would fit that. And really, we're going to do that by R. And we've been discussing a little bit lately and throughout the chapter and last videos about some of the different techniques. First of all, we showed that the regular, usual t-test, the standard t-test, is not adequate in assessing the significance of that slope term because it doesn't take into consideration the correlated errors. The next thing we looked at was the Cochrane-Orcutt. It was an improvement over being able to correctly identify if a trend was truly a trend and not just some temporary pattern. But then the third thing we did, the most recent, was the bootstrap method, the WBG bootstrap method, and that was by far the best performing test to be able to say that slope term, a B1 term, really was significant. If it were significant, that it really did mean that it was a trend that we expected to persist over time. And you'll see that come into play here. So let's go over to the R code, and we're going to look at example 8-2A. So if you're following along in your textbook, you can go to 8-2A. And I'm going to go through this one in detail and then let you work A to B on your own. There's just quite a bit going on in here, so I thought this would be a good place to insert one of the QR codes to kind of help you along here to see what's going on. So as I said, this is called Model A. Example 8-2B will be Model B, but Model A is a realization from a true line. A true line, because why? Well, it's x sub t equals 10 plus 0.1 t. There's your b naught plus b1 t, plus some noise, zt, where this zt can be thought of or modeled by an AR1 with phi1 of 0.9. I want to say something there. I made that sound like it's something it's not. Not modeled by. This is the model. This truly is the model. So not only could ZT be modeled by, it is an AR1 with phi1 of 0.9. Okay, let's generate a realization from that line, from that model, which is a line. It's a line plus noise model. And I don't think we've seen this notation yet. I know we haven't in a video. So we'll call it X1. And we'll say gen for generate, sig plus noise, so signal plus noise dot WGE. Let n be the realization length. There's our B naught, it's 10. We can tell that from the model. Our B1 is 0.1. Our phi is 0.9. That's talking about the ZT term, right? We know it's an AR1. And then give it a seed number. All right, so let's go ahead and run that line. We'll do command int return. It's a neat little command. Don't have to highlight the whole thing. And there is the realization. Now, if you look at that realization, you were to say, yes, that is a line that's going to last forever, I think you're stepping out. You're right, but it's a little risky to make such a claim, right? It is correct because we know what the model looks like, but that's the difficulty that this test has on its hands, trying to determine, is that really a trend that's going to last forever, or is that just some temporary thing that's going to change later? So this is our first chance to really look at this. We've talked about it in some previous videos, just the most recent ones, but now you know what it looks like with real data, and that's an issue. So what did we suggest? Well, we suggested that you don't run the standard t-test. We also suggested that you don't run Cochrane-Orcutt because it's wrong too often as well. What we recommend was that you run the WBG bootstrap test. And that's what we're going to do here. WBG.boot.WGE, hard to say, of whatever the data set is, which we called X1. Now, hold on, let's think about what we're expecting here. it's going to give us a p-value. It's going to give us some other things too, but we care about that p-value because remember, the null hypothesis is that b1 equals 0. That means that the slope is 0. That would mean that there is no trend line. Now, if we reject that null, that means a small p-value, we reject that null, then we're saying, hey, that line is truly a line that we expect to persist. So that's what's at stake here. This is telling us whether or not we should model it by a signal plus noise model. So let's run it, and there is our p-value, PV for p-value. Not to be confused with P, right? That's the order of it. So p-value of 0.03. So that tells us that, yes, since that's less than 0.05, we'll check it at 95% confidence. Let's reject the null, and we're saying that B1 is not 0. B1 is a slope that is significant, and that means we think that this is truly a line plus noise model. Okay, well, once we've made that decision, then what we do is fit a least squares line to that signal term. Well, the signal is the line piece. That's b hat 0 plus b hat 1 times t. Let's do that. We'll call it XA. So SLR for simple linear regression, .WGE of the data set. Here it comes. And among the output, we'll look at each of these outputs in order here, are the B naught hat, the B1 hat, and let's check and see what those are. Says that it's 12. B1 hat, that's the slope term, is 0.059. Notice that's, if I'm rounding that, that's 0.06. That's pretty close to my 0.1, just like, you know, we got B naught of 12. 12 is not too far away from 10, so it's doing a pretty good job there. If you want to look at the residuals, here are the residuals. Just looking at them as a whole doesn't do much for me, but it lets me know they're there. That's a good thing to know. And then it also lets me think about my next step. Well, my next step is that we're going to now fit an AR to those residuals. We've got the line part modeled. It's in this B naught hat and B1 hat. But now we need to fit an AR to those residuals. And how do we do that? Well, that takes us back to some previous things where we're trying to just get the model identification. So AIC.WGE, we're trying to do this for the residuals. We'll let P go from 0 to 5 and let Q go from 0 to 0. In other words, we're making this an AR. So let's run that real fast and see what that gives us. We'll do command return again so I don't have to highlight the whole thing. And then let's look at xi.aic and see what it gives us. And what we see is the final results of the model here. We can tell that the final fitted model should look like this. X of t should be, now this came from the first part, those are the B naught hat and the B1 hat. So 12.028 plus 0.059 t plus z hat t. What's z hat t? Well, that's what we just modeled. We modeled those residuals by that AR, by the AR what? By an AR3, I'm looking at this, P equals 3. There are the phi coefficients, so we know those are going to be important. And there's the variance of the residuals, the variance of the A, sigma squared A is 0.97. So we need those phi coefficients. We need that variance term to say what this model truly is. And so we can see this line right here where you'll see those three coefficients coming in. 1 minus phi 1, which is 0.98, minus negative 0.08, that's plus 0.08 b squared, plus 0.14, so we're writing it in operator notation form, cubed, of z hat t equals AT, and AT has a variance of 0.971. So you can see how all this comes into play. It's really quite sequential. You simply model the line as you would simple linear regression, and then you model the residuals. That spell check is getting in our way. Then you model the residuals with an AR. And that's how you designate, how you write out your entire model. Now, I was doing a lot of talking as we went through that just to show you the sequential nature of what we were doing. But there is a shortcut command that I highly recommend that we use. And I bet you do from now on, now that you know it, or you're about to know it. And it comes from the for forecast, 4.sig+noise.wge. Let's run that and see what we get. We'll call it fit.sig and run it, and there's the plot. Now, you're probably saying, where did that come from? Well, those are forecasts, and that's what this FORE, so the 4 is for forecast. So we were expecting to get forecast, and that's really what we got out of that. So that's more than we needed. You'll see in the next video where we focus on the forecast. That's not the focus of this video. But I'm just giving you this shortcut command where you don't have to go through all of these steps to get to where we got. You can see it straight from here if you'll just put in this command. And then, now you might say, well, that's just the plot. I don't see any of the output. And notice that the output, there's a little bit of it, because if I look at the output, it tells me the 0.98, the minus 0.08, and the minus 0.14. Now, those do ring a bell because those are the coefficients of the residuals. But what about the rest of the model? Well, you can pick it up from each of these lines. Here's our beta naught hat of 12.028. There's our beta 1 hat of 0.059. Here are the phi values. We've already seen those. And here would be the white noise variance of the 0.97. So that's easier, right? Okay, and that is the end of the video, and that's how we fit a line+noise model. As I said, you saw there at the very end, I don't know if you look down at the next line of code, you should now try example 8.2b. That will be model B. Now it's different. The reason that it's different is because it's not a line+noise model. It's an AR2. So hopefully that WBG test, the bootstrap test, will pick up on that, meaning that the p-value better be bigger than 0.05. Because the truth of the matter is that's not a line+noise model. That's an AR2. So give that a try and go through the very same steps we did. The instructions are clearly written out in the text as well, but I want to give you a shot to take a look at that and see if you can reproduce the results that we did in the text. See you next time.